Stephen graduated from the Imperial College in 1970 and studied for a PhD from the University of Bristol. He spent time in the UK, Southeast Asia, and Australia. His work has been on major infrastructure projects and some high-rise buildings, including some of which he will talk about today. Please welcome Stephen.
Thank you, Owen. I spent 24 years trying to reach Australia, 16 of them in Thailand. Some of you will know that Thailand is a Buddhist country. They believe in reincarnation. So I became aware that in a previous life I was a pile, which is why I understand how piles feel and want to probably tell you a little bit about that. So there are a couple of common problems with the design of piles and pile groups. Some of what I'm going to say tonight is aimed particularly at structural engineers. I think there are probably some structural engineers in the audience. I'm sorry you got the wrong career, but never mind, make the best of it. Many engineers seem to think that they can design piles which are either end-bearing piles or floating piles, where floating piles means a pile which takes most of its load in shaft friction. Unfortunately, only God can decide whether a pile will be a floating pile or an end-bearing pile. With all due respect, the Director General of Main Modes can't, and neither can you, because it depends upon the loads and on the elasticity. So I understand that despite the fact that we've had limit state design codes in Australia for quite a long time now, a lot of pile design is still done on working stress design. So let's go along with that, and we'll calculate the ultimate pile resistance in shaft friction and end bearing. We'll add them together. We'll divide by a factor of safety of 2.5, which gives us an allowable load. But the issue is, can we add the ultimate shaft friction and the ultimate end bearing? Let's have a look at a simple board pile. 1 meter diameter pile, so the load settlement curve might look like something like that. So the shaft friction will increase, and then it'll reach a point at which the shaft friction won't increase anymore, and we'll get effectively settlement of the pile with no further increase in load. And that will happen at about 0.5% of the pile diameter, or about 5 mil. Now let's consider the base, and that's a typical sort of base load curve, and we can then we'll add the two together because we think we can, and we'll get something that looks like that. So the green curve there looks reasonably like the sort of load settlement curve that you might get in a static load test. The problem is that our maximum shaft friction has occurred at about 0.5% of the diameter deflection. The maximum end bearing probably doesn't occur at all. There's actually no evidence that the end bearing load will reach a limiting value. It'll go on increasing slowly the further you push the pile down into the ground. But let's say we're going to stop at 10% of the pile diameter, or about 100 mil. So we've got a maximum shaft friction at 5 mil, we've got a maximum end bearing at 100 mil, and we're adding them together. Can we add them together? Of course, if the soil is linear elastic, perfectly plastic, and behaves something like this, we probably can add them together. But does soil behave like that? Does steel behave like that? I mean, what materials actually have linear elastic, perfectly plastic behavior? I don't think there are any. So is it logical to add together two components of resistance, a maximum end bearing and a maximum shaft friction, which actually cannot coexist? I don't think it is. And therefore, we're not reliably modeling this ultimate resistance. And the resistance at the working load, where we've divided by 2.5, is a function of the very non-linear load displacement relationships, and therefore it's also non-linear. And we'll have a much higher shaft friction load at small displacement than the end-bearing component. Now, Let's look at a single pile, and I'll take a real example. If you happen to drive over the beautiful go-between bridge, please have a look at the piles. I designed them. They're some of the best in the world. But on the south side, there is a tolling gantry, and that's standing on some wonderful piles. They're, I think they're 24.5 meters long, 1.2 meters diameter. Because they're main roads piles, they've got a permanent steel casing, 24 meters long, and the socket out of the bottom to carry all the weight of this tolling gantry is about 0.5 meter long into the weathered phyllite. But, of course, main roads say you've got to have a permanent steel liner, and there's no shaft friction on the outside of that liner, which means that the load distribution down the pile will look something like that. You've got the same load on the top as you've got at the bottom of the liner because there's no shaft friction, and then you've got a little bit of shaft friction and some end bearing in this 0.5 meter deep socket. That's the design. But what happens in practice? In practice, we put a little bit of load on the top. That load causes that pile to shorten elastically because it's an elastic material. That means that the pile is moving relative to the soil, and that means we're going to get a little bit of shaft friction, actually enough to support that bit of load. As we increase the load, this shaft friction will gradually increase until at some point we'll reach a limit on the shaft friction, but we'll get a load distribution that looks something like that, and that's probably the working load. So at the working load, although we've designed for some sort of ultimate load with shaft friction and end bearing, at the working load, the load isn't going to reach the toe of the pile at all. So the way that we normally design piles actually bears no relation to the way that they actually perform. And this creates challenges for us because when we're doing limit state design, we now know that the serviceability limit state will generally control the pile design, and the serviceability limit state needs us to understand how the pile is going to perform. So we're not doing very well there. Now let's look at pile groups, because this will make life easier, won't it? I'm going to talk about a job that I was involved with in Bangkok, a residential tower. Bangkok is on the floodplain of the Chao Phraya River. There's lots of rock, just like there is around Queensland, but it's all at least 1,000 meters below ground. So we don't have many piles to rock in Bangkok. There are these alternating layers of clay and sand, clay and sand. These aquifers are shown down to about 600 meters, but those are the ones they pump water out of. They do go on deeper. There was a requirement to build a 40-story tower on a square foundation, and the concept was for it to be an RC frame structure. The structural engineer decided that the foundation would be equally spaced, board piles, about 55 meters deep, and he said, okay, I'm going to determine the pile load by taking the total load of the building and dividing by the number of piles. A very simple approach that says all the piles are uniformly loaded, just an executive decision. The piles were installed, the sheet piles were installed, the excavation for the pile cap was completed, the piles were cut down, the rebar was fixed, and then the client said, I don't think I want an RC frame structure, I want a steel frame structure. And he went off to somebody in Singapore to give him a D&C contract for a steel frame structure, and they employed a local structural engineer, and he said, oh, there's a problem here. When I analyze the loads coming down the core, the piles under that foundation that's already in the ground are overloaded. And the original designer said, don't talk BS. I designed these piles for an RC frame structure, which is obviously much heavier than a steel frame structure. Of course they're all right. And I was called in to referee in this dispute. Well, the first designer had certainly ignored any group effects. He just said all the piles are equally loaded. The second designer was using the SAFE program, which some of you may be familiar with. It's a module of the ETABS structural software. And of course, like most structural software, it says that piles are linear elastic springs on an infinitely rigid base. A nice, very simple mathematical model that fits into a program very conveniently, and it doesn't bear any relationship to how piles actually perform. So I started, first of all, I was given a couple of load settlement curves, and I saw that they, for a start, were nonlinear. So I put decreasing stiffness with increasing deflection and load into the springs in the SAFE model, but that wasn't enough to reduce the loads under the core to meet the requirement. So I then looked at the loading, and the picture at the bottom here is a sort of distribution of the loading across the building, and I had to do all this manually, that is with my hands, and I did some hand calculations and calculated the settlement of an elastic foundation on an elastic soil for each of those 4 increments of load. And then I added the settlement curves together to give me a guesstimate of the total settlement of an elastic foundation under that load. And then I said, well, it's not an elastic foundation. The structure has got some stiffness, and I arbitrarily took about 30% of the total settlement to account for the structural stiffness. And I applied that settlement to each pile position, so that under this 40-meter square mat, we had lots of piles, and there was a separate spring stiffness calculated for each pile. And when we did that, there was no overload at the core, the dishing of the mat was reasonable, and everybody went away happy. The second project I want to talk about is another job in Bangkok, but this time for a rather higher structure, 3 70-story high, over 200-meter high towers sitting side by side on a common foundation. It's not a raft foundation. Bangkok, the surface soils are too soft to allow you to use an actual ground-bearing raft foundation, so it's a piled mat foundation. There are actually 399 piles under that main structure. This gives a little picture of the towers over here, and then some podium structure and other things. This is a detail of the soil profile with alternating layers. The hatching is clay layers, and the dots are sand layers for boreholes that went down 80 meters. So like a licorice all sort of different layers of sand and clay for 80 meters. The column loads and the lift cores were laid out in plan, and the dead loads and the live loads were estimated. Structural model was created. Again, piles as linear elastic springs on a rigid base. And of course, the greatest pile loads were under the cores. The cores you can see there for the 3 separate towers. Obviously, these are the columns, and the 399 equilaterally spaced piles. When the SAFE program was run, obviously, if you analyze this as linear elastic springs on a rigid base, then this is what you're going to get. You're going to get the maximum settlement under the 3 cores, and obviously, because of interaction, you'll get maximum under the middle one. And because they're linear elastic springs on a rigid base, the pile load distribution will be exactly the same. It's just multiplied by a factor. This is what the structural engineer came with and said, okay, this is what the pile loads will be. And I said, no, they won't. And I ran a program called Piglet, which is a very simple program. It only allows you to choose either an infinitely rigid structure or a fully flexible structure, but it takes account of the soil flexibility, and it also takes account of the effect of the load from one pile being shed onto the next pile. So this is saying that if you have an infinitely rigid foundation, then the highest loads are going to be actually all around the edges, and the lowest loads are going to be in the middle. Exactly the opposite of the linear elastic spring on a rigid base safe model. If we then say, okay, well, let's say it's a flexible foundation, in Piglet we get this answer. So this is pile loads, where we are seeing the maximum load in the center, and the settlement curve looks something like this, but it's much higher settlement than the safe model has predicted, because we're allowing for the flexibility of the soil, and we're also allowing for pile-soil-pile interaction. So the real mat foundation is going to have stiffness somewhere between flexible and rigid, somewhere in between. But the big issue is, whereabouts is it going to come? We made 3 different runs of SAFE with different proportions of stiffness. This was the stiffest one, and the differential settlement you can see at the bottom was between 25 and 62 millimeters. The middle stiffness gave us slightly higher displacement at the center, and the most flexible foundation gave us a higher deflection at the center again. This was the distribution the other way. So now we can see that because the structure is relatively stiff in this direction, the highest loads are actually at the edges this way, but because the structure is more flexible in the longitudinal direction, then the distribution the other way is the opposite. So given this project and construction about to start, we took the opportunity to actually take some measurements. And out of those 399 piles, we instrumented 15 of them with vibrating wire strain gauges at the top. Their locations were distributed like those red circles that you can see, so a reasonable distribution across the whole foundation. We cored holes in the top of the pile. We took the piece of core away and tested it in the laboratory to determine the modulus. We put a sister bar with a vibrating wire strain gauge into it, and we grouted it in and took the cables away to an instrument house. In addition to measuring the load in the piles, we measured the settlement of the base slab during construction. The engineer nominated 45 points for survey, but it's a construction job, it's in a basement. They couldn't all be seen by the surveyor every time, but the ones that could be seen most of the time had that sort of distribution. So the results here of the pile load, red is the highest load, so you can see that the measured load was highest at the beginning in this corner, and we are certainly getting lower loads under the potential lift cores. As the building went up, again, we've got the highest loads in the red areas and lowest loads still in the middle. So exactly the opposite of the linear elastic spring on rigid base model. And here we're getting up to over 8,000 kilonewtons on each pile, but still the lowest loads in the middle. These are the individual pile strain readings plotted against time. The black line here is the height of the building, just plotted as floors. So it goes up to about 70 floors. These black diamonds represent the strain that would be expected in the pile if all of the load of the building went onto the piles. And you can see that it obviously wasn't going onto the piles at the early stage. The red squares, if you can just about make them out there, are what the strain in the piles would be expected to be if about 80 to 100 kPa was initially taken as a raft foundation. So you couldn't design for that because the surface of Bangkok is subsiding, as I'll come to in a minute. But in reality, in the early stages of construction, that foundation would be bearing on the ground. And those red squares give a reasonable match with the measured increase in strain. This is the settlement of the slab in February of 2008, and we can see that it varies from about 18 millimeters in the red part to about 40 millimeters in the center. It changes, to this in June, this in August, and this in September. And if you look at these numbers here, one thing that if you're good at mental arithmetic, which I'm sure you all are, the differential settlement there is 33, there is 33, and there is 33. So the amount of dishing of the raft actually remained the same as the whole raft then was going down as the building went up. This is the result of all of the settlement points. The bold lines here, green and blue, that's the height of the building in floors. So we can see that the settlement of the building really followed pretty much the application of load. This is where it was topped out. This would be additional settlement during fit out and so on as the building increased in its dead load. I mentioned that the surface of Bangkok settles. It's due to water extraction from those various aquifers. So this is a footbridge just up the road from the site. That was the bottom step that was originally cast on the ground. That is the driven pile that the footbridge is standing on. For some time, you were able to step up onto the bottom step, but in time, I'm afraid, a step to help you to get up onto the bottom step was needed. It's settling typically about 20 millimeters a year. So that's the ground surface is continually going down, and a building on deep piles will, like this, not be going down. So we just need to keep that in the back of our minds. We did an instrumented static load test, and I foolishly made a Class A prediction, which is that gray line. So that was what, based on the site investigation and my design, I said I think the load settlement curve will look like this. The yellowish line is what it actually, how it actually behaved. So my design was a little bit conservative. I then, just last year, decided to be clever and do some finite element modeling using a geotechnical program called Plaxis. So first of all, I started off with an axisymmetric model, trying to model the static load test. And the green curve there and the gray dots are what we had before. This is what's called a semset analysis, which uses a hyperbolic relationship and gives a very good match. But the blue dots, that's my Plaxis model, which I felt was pretty good, gave me reasonable confidence that the soil layering that I'd got in my model was matching with reality. So I then got foolish and extended that to a plane strain model to look at a slice through this foundation. This is what this matte foundation, 4 meters thick, looked like. This is how it fitted in the Plaxis model. And the green layers there, this is how I decided to try and model the building. The density of those layers is adjusted to match the weight of the building. And the idea was that the stiffness of that would increase as the depth of it has increased, to try and model somehow the stiffness of the building increasing as it's gone up. This is the first stage of loading, and you can see that things have started to move down. And this is the full load now, the deformed mesh for the full building load. This is actually quite interesting because this is what the finite element model says the pile load distribution across the section will look like. And you can see that these piles at the edge are carrying a lot of load, and these piles in the middle are carrying very much less load, exactly as Piglet was predicting, and not what you will get from a linear elastic spring on a rigid base model, because all of this block of soil and piles is going down together. Therefore, you're not getting relative movement between the pile and the soil in order to generate shaft friction to support a load. So the load goes to the edges where there is more relative movement. This is, came from the model as well. So the dashed curve is the measured settlement dishing across the short axis. The black line down here is the Plaxis model that shows I've still got my stiffnesses wrong. The building stiffness is too high, and I need to reduce that in order to try and get something that matches that more closely. If you look carefully in there, you might just about see this red curve. That's the finite element model of the settlement under all those stages of loading. So I think that really follows the trends of the measured settlement quite well. I felt quite happy with that, and therefore I made an extrapolation of how much more settlement there would be due to consolidation of these deep clay layers, and that was out to the end of, or sometime in 2014. I presented a paper on this in the Soil Mechanics Conference in Seoul 2 months ago, and just over a year ago, in preparation for that, I was surprised to find that the client had carried on measuring the settlement. So we actually had settlement measurements up until April last year, with the construction finishing back here. So quite remarkable that we've got settlement measurements that long after the end of construction, and the FE model is in there, which again, I mean, you can give me a round of applause if you want, I don't mind, but I think that's, I'm very happy with that match. So, just to show that things haven't changed all that much, the next picture will show you a suggested bearing pressure for a raft here in southeast Queensland using linear elastic springs on a rigid base, and there it is with the maximum settlement, maximum pile load going to be in the middle, and I'm sorry, that's wrong. So it's unlikely to be a realistic model of the ground pressure or of the pile loads, nor will it have the correct curvature for determination of bending moments and reinforcement requirements. So if you want the answers to your problems, there is my phone number and my email address, and thank you very much.
Thank you, Stephen.